Well, good day everyone. Once again, you are welcome back to this my YouTube page. So in the second, this video is a continuation to the previous video you have watched about the common emitter transistor configuration. That is, in the previous video you have watched how we did the input characteristic. Now we want to look at the output characteristic curve. Remember what I told you in the previous video? When we were doing the input characteristic, we concentrated our values. We are measuring the value of IB with this, that is the input current to the transistor and the input voltage to the transistor, while we kept the output voltage of the transistor constant. So in this case, in the case of output characteristic, we'll be measuring the output current of the transistor and the output voltage of the transistor while we maintain a constant base current. So how do we do that? To maintain a constant base current, we use VBB to adjust and readjust base current. We use VCC to give us different values for IC and IE. So let's look at the procedures from the manual. Say connect the circuit as shown in the circuit diagram. Keep emitter current IB at 20 microamp by varying VB. Varying VCC gradually in step of 1 up to 12 volt, and note down the collector current IC and collector emitter voltage VCE. So repeat the above procedures for IB equal to 60 and 0 microamps. So let's quickly, without wasting much time, launch into the experiment. So we want to now have equally prepare the Excel sheet. So we are starting from IB equal to 0. Okay, the little modification I did when I was carrying out the experiment, I used IB at 0, IB at 12 microamps, and IB at 40 microamps, at 0, at 12, and at 40. So we measure VCC, we measure VCE and IC, that is collector emitter voltage, which is the output voltage, and the collector current, which is the output current. This is VCC value that we have set. So let's go to the experiment. When VCC is equal to 0, so remember, where is our VCC? This is our VCC. This voltage is measuring VCC. So let me try to label them for easy identification. This is VCC. This voltage is measuring VCC. Okay. So this is VCC voltage supply. But the actual voltage that comes out is to be measured by this. So this is our VCE. This is our VCE, collector emitter voltage, and this is our VBE, base emitter voltage. Then this is IC. This one will give us IB, sorry, and this will give us our IC, the collector current. So in the output characteristic of our interest is to measure IC and VCE, keeping IB constant. So as usual, let's start from the lowest value. I'm starting here from 0%. We want to give IB a current of 0 microamps. I want to start our experiment by varying VCC. So as usual, just like a repeat of what we did, but it's just like in the opposite direction now. So we want to start, let me take it to the lowest value so we can take our readings. So from the table we have gotten, when VCC is equal to 0, everything should be 0. When VCC is equal to 0, everything is equal to 0. Our IC is equal to 0, and our VCE equals to 0. Let's say forget, let me change this ammeter range to become a microamps so that we will not miss any current, because at times if smaller current is flowing that milliammeter cannot measure, the system may be telling you that 0 current. Meanwhile, very small microammeter range current is flowing. So we have done for 0, everything is 0. Then we adjust this value. So when VCC is equal to 0.12, what do we get? When VCC equal to 0.12, we get 0 and then 0.12. So we go to the table and record the 0.12 is VCE, 0 is IC. We go back to the experiment, we adjust it again. When VCE is equal to 0.24, our IC is equal to 0. So but always keep tab of this guy IB. Once you see that the value changes, you have to revert back, use a VBB to correct it back to the value where you have set it. So we record the value as usual in our graph at 0.24. Everything is still 0. At 0.36, let's get at 0.36, everything is still 0. That's IC is equal to 0, VC is equal to 0.36. So this simply means that the transistor is not yet biased. Remember that this kind of configuration, it means the emitter base, remember this is an NPN transistor, the base is positive, the emitter is negative. So it means emitter base is reversed, is not biased yet. Remember, the configuration of a transistor is that input section is always forward biased, while the output section is reverse biased. And when you look at the connection, the positive terminal of the battery is one way or the other connected to the base. The base is the positive, is the P type, while the emitter is an N type. So this is a forward bias condition. But the voltage that this transistor is receiving is not enough to set it up for operation. That is why you see that all the voltage generated by VCC is dropped at the base emitter terminal. No current is flowing through the transistor yet. That's why you see this guy recording 0 and this guy recording 0. So let's go to this other part at 0.3600. So at 0.48, still the same thing, 0 0. At 0.6, still the same thing, 0 0. At 0.72, still the same thing, 0 0. At 0.84, still the same thing, 0.96, 0.1. Okay, when exactly did the current start flowing? Okay, I think we have started seeing current at 1.92. So at 1.92, let me see. So at current start flowing here at 0.36. So let's see what happened here at 0.36. What happened? What was the current? 0.36. At 0.36. At 0.36. Okay. Let me check something. Could it be because of this? Could it be that this ground is giving me an headache here? At 0.36, I think we're seeing current. We are seeing the current because of the ground. That's why you are not seeing any current here. So as at 0.36 and at 0.236, this is the current flowing. At 0.48, 0.5. But always keeping tab at this. Anytime you want to leave 0.0 that you have set, you can easily use this guy to set it back to 0. Okay, it has set it back to 0.01, so almost at 0. So once whatever you get, you record your values. That is for IB at 0, and you change your IB to 12 microamps. How do we achieve that? Go to the Pro Tools. IB at what? At what value? We need IB at 12 microamps. So we try to increase VBB 12 microamps to something around 12 microamps. So this is 12.6. Let me take this guy to the lowest value, 12.6. Let's see whether we can. Okay, I think we are able to get 12.1. So we leave this guy at 12.1 IB, and we begin to vary. So at 12.1, now what is the value? You see that 0.03 is the current that flows here, that flows at the VCE. Then 82.2 microamps is what flows at the collector current. You record the value. So at the VCE is equal to 12 volts. So then at, so I think the IB change. So we try to set it back. So 13, 11.8 is close to 13, so we can still leave it like this. So you record this value 0.03. Then at 0.05 we get this, we get 181 and 0.5. So you try to set this thing close back to 12 microamps. So 11.7 is the closest to 12. So this is 12.8. 11.7 is just like 3 points to 12. Okay, so we can leave it like this and take a measurement. So this is how we are going to do it to get the value for IB is equal to 12 microamps. And when you are done with that, you go to the experiment again. When you have taken all your desired number of points, you set this guy to 40 microamps. 40 microamps. 40 microamps is what we need. 40 microamps. 40, 39, 40.2. So 40.2. So we are starting the experiment from 0. At 0, what is the current that flows? At 0, voltage is 0. Now there's a current of 5.28 microamps. You record it. Then at 0.2, what is the current that flows? You record your current and the voltage. 39.1, 40.3. So 40.3 is still equal to, it's still close to 40. So it's not up to 1. So you take the reading of IC and VCE. You alter it again at VCE of 0.03. You get 201 microamps. You record it. So you do that for all the values that you have set, and when you have done that, you get a table of value like this. So just like what we did in the previous video, that is in the case of input characteristic, to plot the graph is simple. Like I always say, it's just a matter of drawing this. These are the values you want to plot. These are the 4 values you want to plot. When you select all of them, go to your insert and plot your graph. Very simple. The automation has made everything easy. So you can use a point, you can use a thick line, anyone you like. So I think I want to try this. This looks a bit awesome. So you can increase. Now when you look at it, you see that there was a kind of a little bit of flop here. That's due to maybe error in the measurement. If you check this value, if you check this graph and the theoretical shape that we are expecting, you will see that it is closely related. This is the output characteristic curve for the common emitter configuration. Now look at this shape and compare it to what we are able to get. You see that it's almost the same thing. So this is output characteristic curve. So from the output characteristic curve, we can now find the other parameters. We can find the reverse voltage gain, forward current gain. Forward current gain is I2 over I1. Reverse voltage gain is V1 over V2. That is input voltage over input current at a constant base current. So that is all about transistor configuration. So let's quickly look at where HRE. I say HRE is change in VEB over change in VCE at constant IB. So you go and check VCE at constant IB. Where do you have IB that is constant? That's constant base current. So that is, you are making use of this particular table now at constant base current. So let me delete one of these so that we can see the screen very well. At constant base current, change in VCE, change in VEB over change in VCE. So this is VEB, that's a base emitter voltage. Then change in VCE. So if you check this, you see that this is V83. Where do I get this? 83 cell. Okay, that's so if you check the curve at this point, you get the value. You can pick this particular curve that is having a color green. If you place your cursor here, you get a value of 83.8300. Then at this point, what do you get? I think I got my 83 point something around here. So but you mustn't use the exact, just find the slope of this. That's just what we're trying to do, just a matter of finding the slope. So you can decide to choose, and you know when you want to find the slope, you have to look at the linear part of the curve. This is the linear part. This one now, the slope of this part is 0 because there is no change in the y axis. but where you have a linear path is where you can find the slope. That's why I'm putting this point and this point. So if I put this, so whatever value I pick here, that's 83,000. If I pick the second point here, 41,400. So that will be y2 minus y1. Then what's the value is 0.24. What's the x-axis value is 0.6. So when you calculate it like that, you get this particular value. So let me try to make it a bit visible. So that will give you your HRA, change in VEB over change in VCE. So when you do the calculation, you get 583.33. Now, reverse voltage gain has no unit. Gain has no unit because it's a ratio of voltage to voltage. So that's 583. You see that compared to what we got for the case of input impedance. Input impedance is always high. Output impedance, that is reverse voltage gain, the gain is a bit low. The voltage of a ratio of input voltage to output voltage. So that is for reverse voltage gain. Then the other one is a forward current gain, HFE. HFE is IC over IB at constant VCE. At constant VCE. So that means we are going to use the first value, the first so at constant VCE. So at constant VCE, that's where we now make use of IC over VCE. So you just pick a current from the table. If you pick this particular value over VCE, it will give you your, what do we call it, will give you your forward current gain. So that is that about that. Then the last one is HOE, that is output admittance, which is IC over VCE. Just pick a value from the curve where you have a curve of IC versus VCE. Then you plot the voltage. I mean you use the value of the voltage VCE, so you get your HOE. So at the end of the day, for this transistor BC107 that we used, the parameter value that we got are number one, HIE, which is 1128.6 ohms, 1128.6 ohm. HIE is HIE, which is 1128.6 ohm, 1128.6 ohms. Then HIE, that's the HIE. This one is not correct, so let me delete this. HIE is, so our HIE is 1128.6 ohm, and our HOE, 1 over HOE, which is the output admittance, is 12.42 Siemens. That's it. The unit of admittance is a Siemens. Okay. Then the last one, which is a HRO, reverse voltage gain, is 583.33. No unit. Voltage gain does not have unit. Current gain does not have unit. Reverse voltage gain doesn't have units. Forward current gain doesn't have unit. That is a HFE. Then the only one that have a unit is resistance and admittance. So that will be all for common emitter transistor. So we have done the input characteristic, we have done the output characteristic, and we have been able to see how we can plot the graph and use our graph to find the input parameters of this system. That will be all for now. Thank you very much for listening. Please do subscribe to my YouTube channel. Click the notification button to get updated video. Click on subscribe, and make sure you watch this video and recommend this video to your friends and your colleagues. Thank you very much.